like so far we introduced somehow by some example the diagrammatic perturbation theory. So let's just state some general aspects of the diagrammatic approach. So the diagrammatic approach, once you come also to higher orders, what you will see is that this is great help to calculate, higher order correlation functions or endpoint functions, because it somehow allows you more directly, to calculate this Wick construction in more pictorial, way, more pictorial, I don't know way, so it makes it more easy, and also it's easier to look at like the combinatorial factors sometimes, and okay, this is, you will see while doing it. So diagrammatic approach helps to efficiently represent perturbative expansion. And the way we do it is you draw the nth order diagrams or graphs. That's what we did, for example, for two-point correlation function in first order. And then once you have done all the drawing, you translate them back into analytical expressions. Meaning that each diagram is expressed then again by an analytic expression corresponding to the individual graph. And this is done, it's like now, or just write down the way how it is in a couple of rules or steps one can do this. Now, just one more comment. So, if you would just do the brute force calculation of all the big contracts, you will see that you generate often the same contribution. So, the diagrammatic way, you can more easily see what is the combinatorial factor. But in practice, it's sometimes also hard because you can make errors or mistakes on the combinatorial factor. So when it becomes more involved, it sometimes also requires some thinking to get all the combinatorics right. And also then you have to watch out that you don't miss any diagrams and so on. So again, it also needs some practice, but once you got used to it a little bit, it should really simplify your life. So translating back, we said is what you do is you attach coordinates to all field vertices. So this was like the external x, got some fixed coordinates, and the internal vertices, some coordinates that were integrated over. So attach coordinates to all field vertices. The first step. Then what we did is to identify the lines connecting two points, coordinate points with the free Green's function. So identify lines between two points with the free Green's function. Yeah. Green's functions, and then what one has to do is one keeps the external x with coordinates fixed, but you integrate over all the internal coordinates and describes the interaction vertices here. And then there's the issue of the sign factors that will still be discussed. But as I've already said, so this is just some general guidelines how one should proceed, but there is no really fixed way, canonical way how you have to do this and how you have to draw the diagram. So there's some flexibility there, so there's no fixed rule how to draw a diagram. And actually people will draw different diagrams differently, and to see that two diagrams are the same, any kind of reshaping or twisting or rotating of the diagram is allowed, as long as you don't really change the diagram, that is, as long as you don't cut any lines. Okay, so we had already seen an example. I mean, you can draw the one diagram that I drew this way. You can, I mean, also draw this way if you like, or of course, you can also just twist the diagram or rotate the diagram or twist this interaction line if you like to draw this. Yeah, this is somehow bad because this could be confused with a second order process where you have two interaction lines. But this is all allowed, okay? So, now, this also means, as I already said, that if you come to higher orders, it can be sometimes that you draw two diagrams and then only later on realize that they are actually the same. You just drew them in different ways, but they can be deformed one into the other. Okay? So then it's just we need to define some more wordings for diagrams, some terms. And this I will do now. Can differentiate between diagrams having different properties, and these properties I will now mention. And again, the best thing I think is to look at some example. So let me just draw some diagrams that appear in second order, and then once we have drawn the diagrams, we can see that they have like different properties, and we will just name the properties. Okay. So let's look at, let's call this internal structures of diagrams. In this example, just consider what we said would, for example, appear in second order perturbation theory. So we said, well, there are terms that have to be calculated this way. Okay, so this was like what we said, oh, this is quite a lot, and this is a lot. This would correspond to, what did we say? So this is 8, so to 10 operators. So we have 5 creation, 5 elimination operators. So 5 faculty was 120. So we should find 120 diagrams if we look at this. So let's just diagrammatically look at what this corresponds to. So we would draw this way. So we have the two interaction vertices, and then we have two external lines. Okay, so we would have to form all the diagrams we can out of these lines. Now actually, I spent some time and just drew all the 120 diagrams, so I started and it's really, it's a good exercise because like I was getting some combinatorial factors wrong and missed some diagrams, so it took me a while to get them all. So I actually just, in the break, thought I would use the break to draw all the diagrams, but then I think it doesn't make too much sense because it gets quite involved. So we will make an exercise for maybe a bosonic theory. So this is all for Fermions where it gets a little bit like the number of different diagrams can be simpler, can be less, so probably we'll discuss this. But whoever wants to find all the 120 diagrams, I'm happy if you try. And so I think I found all of them, so we can afterwards compare. So if you want to do this like over the next week or whatever, just do it. But let's see like what would be terms that appear. So one can try to organize this in the following way. So you have to connect all the different contributions. So one option is always to let's first start connecting these two. Okay? So this is, I'm just now, instead of doing it systematically, I just give examples. So we can connect these two, there's only one way to do this. And then we would now be able to connect these. Okay, so there's again two options that we can look at. We can first keep all of them separated. So we can connect these among themselves and these among themselves and later on look at the connections. Okay? So if we connect these among themselves, well, we have the two options that we discussed already before, and here's the two options that we discussed before. So this would give rise to 4 different diagrams. No? And we just write them or draw the one. So this would be one possibility. So then we would have, we said we have this possibility. Okay, so I should careful with the drawing. If you cannot identify the drawing, let me know. Okay, so this would be like 4 different diagrams that we end up with. This one, and there's 2 ways to do this one. Then you can take the first one and make it this shape, or you take the second one to make it this shape. So this would be already 4 diagrams. Now, what we can also do is we can, well, still take this diagram, these 2 legs connect the external legs, and then combine these 2. Okay, so one way would be to take this one and connect this with this one, taking always nearby legs and then making these 2 loops. Okay, this would lead to a diagram of this type. Okay, so this would be just, for example, connecting this way, this way. So now we can ask about, so how many ways do we have to actually draw this diagram? So then we can just, combinatorics is always dangerous because sometimes you can get it completely wrong, but like here you can see that, well, how many ways do you have to do? You can do it. Well, you can take 2, just connect them this way, you can connect them this way, or you can connect them this way. So you have 2 options here and 2 options here. So this will give you a factor 4. Okay? This would be one option. Now the other option would be to just take one off top of the other. Okay? And then connect them instead of like this way in the other way in the ring. Okay? And this then will lead to, well actually, this diagram here. This wall components again. This would correspond to taking this on top of this, and then connecting this line like this, and this then becomes a straight line. This is this line, and this straight line is connected to this straight straight line here. So this would be these two arrows here. And here you connect just the downer once again like this. And again, you have just 4 options. Now you can take this like this, or this, and this like this, or this. This would give you a factor 4. Okay, so this would be another example. Now, what you can also do is you can, for example, let's see, you can draw these diagrams a little bit different. Like this. I mean, we're talking about how to connect these, okay? And then you can just attach them like this. You get 2 loops here. Now, how many options do you have? You could say, well, I have 2 options here and 2 options here, but then I would have 4. But then you already made a mistake because you're overcounting. Because like this one taking and this one, and then you say, well, you can take it this way, or you can take it this way, but this is the same contribution because you can just, transform the one into the other. Okay? So you just have 2 options, namely connecting them like this or connecting them like this. This would correspond to this, and this would correspond to twisting both of them. Okay? So this would give you a factor, let's say, 2 for this diagram here. Well, and then there's other options. You can just connect again these 2. So I found how many more? Two other diagrams to connect these 2. Okay, and then you can take diagrams where you say, let's just connect this external line, not among them, but just connect them to one diagram. And connect them to one diagram and keep the other diagram just isolated. Okay, so keeping the one diagram isolated. We already said, well, there's 2 options. It can be done this way, or it can be done or it can be done this way. Did I mention this already? Okay, so this would be the 2 possibilities. So what we said, let's take diagrams where we connect these 2 legs to this and keep the one isolated. So there's a combinatorial factor of 2, which allows us, which means allowing us, let's take this isolated or let's take this isolated. Okay, so that's the 2. Now this has to multiply with the diagrams. We can connect with these external lines with this, but this is already what we did now in the one part of the means function. So this gives us the... Okay, I just write it now down. I hope you understand. We said we have 2 options, 2 possible diagrams, both with a factor of 2, how to connect 2 external legs to one internal. So what I mean here, you get, instead of, here actually this would be 2 types of different diagrams. This times this and this times this. Okay? And here we have the same. There. Okay, so this would be examples of the diagrams where we said let's connect these to just one vertex. Now there's no possibility to connect this to one vertex, interaction vertex, and this to another interaction vertex without then connecting these 2, no? Because this would then lead to the diagrams that would be connecting all with all of them, okay? Let me just see. So, actually here I wrote down all of the diagrams. Here there's still like 2 type of diagrams that I didn't mention. Here I wrote down all of them again. So if you want to do it at home, you should look for 2 more here of this type. And then there is several, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways you can connect all of them internally. 10 different ways, but I just draw different ones to then, let's see, make structure clear. Okay, let me just draw some of them here. So one way to connect all of them, well, you connect this, let's say, to this one here, then connect one of the legs to this one here, let's say in a way that you connect this to this, then you form here a bubble, and the remaining one to this one. Okay, this would be one option that you arrive at. Let's see. Does anyone has suggestions for the combinatorial factor? How many ways do you have to do? So you can attach this one to 1, 2, 3, 4. Okay, 4. Now once you connected this to 4, let's say you connected this to this, you have to make it, to make the diagram that I draw, you have to take this one here and connect it to one of these ongoing. So you have two options to draw this to an ingoing. Once you drew this, let's say, to this ingoing, you know that you have to make this to a loop, so this is again fixed. Okay, so the first gives you 4 contributions, 4 possibilities, and then the remaining one is, gives you like 2 options, so you get an overall factor of 8. Okay, so this would be coming with a factor of 8. Then you have, well, you have a similar diagram. Well, this in a way is just generalizing this one. Also, you can also do the same game with this one. Okay. So you have these kind of diagrams. Then you can, well, combine these twos where you have like this combined with this and so on, of course. Then you can have diagrams. Just one example where start building them on top of each other, and a similar diagram would be this one here. And well, you can have this one here where you have the lines crossing, so this would come with the actually all of them come with factors 8. You can have this kind of diagrams, which could not be transformed into this one here, because now you have the legs crossing. No, you would have to do some, you could do some twisting here, but then it would just look differently, but you cannot deform this one and this one. And maybe one more, you can have something like, yeah, this was the one I missed somehow, this took me some time to find this, like you can have these kind of diagrams also. And so on. So, if you want to go through it, you should find 10 of them, and all should have a combinatorial factor of 5. Okay? So you can see, I mean, it takes some time, but you can work out all the 120 diagrams. And I mean, there's always some thinking, and you can easily make errors here, but it's possible to do. Now, writing down this was what was written here, like the 10 operators, and doing all the contractions by hand, I think just, I mean, this is insane, but this is doable. Okay, so if you like, you can do it. But why I did all the exercise is actually to now introduce some wordings, like how we can talk about different diagrams, so we can distinguish. So you see already, like if you look at them, well, there's different types of diagrams that appear. For example, the first thing that you can do is you can distinguish between those diagrams which consist of different parts, like this would correspond to 3 parts. Which one? This would correspond to 3 parts. This here would correspond to 2 disconnected parts, and this would be diagrams that are completely connected. Okay, so this is one thing that one wants to introduce, the notion of connected diagrams. Okay, so this will be very helpful because we will see that connected diagrams will play a special role. So I think, yeah, we come to this next lecture that actually in the end there's another nice thing that in the end one only has to take care of connected diagrams. Like we come to this. So it's clear what is meant by connected diagrams, no? So these are not connected. Connected is if all of the parts are just semi-connected. So then we can introduce the notion of one particle irreducible diagrams. And let me just write down what this means. So one particle irreducible means that, do you know this kind of thing also? Did you? Okay, so I don't have to go too much. So this means that the core portion, let's say, of the diagram, which is defined as the diagram after you take off the external legs. Okay, so for example, here you take off the external legs and you stay with this region. Here's the core portion. Here the core portion would be this part here that you obtain after taking off the legs. The core portion content of diagram after legs containing the external vertices or the points. External vertices have been removed. So the one particle irreducible are defined maybe I should first define the one particle reducible. So the one particle reducible are those where the core portion can be cut into two pieces with a single cut. Can be cut into two pieces, just cutting one line. A single cut. One line. Okay, so let's look at an example. So for example, here if we take the core portion of the diagram would be this here. So if we just cut this line here, we have a non-connected diagram anymore, so this would be one particle reducible. Okay? So if on the other hand, for example, we look at this diagram, we take off the external legs, we see that cutting this line or cutting this line or cutting this line, the diagram still stays connected. So it's here one particle irreducible. This again, like, of course, would be one particle reducible and so on. Okay? So this is the one particle reducible. Now diagrams that are not one particle reducible are one particle irreducible. Okay? So this concept can be generalized to n particle reducible or irreducible, just meaning how many lines you need to cut them. Like if I take this diagram here, how many cuts do we need to separate this into two? We need two, no? We have to cut this line and this line. So this would be two particle reducible. Now this, on the other hand, how many lines would you need? Well, cutting just one doesn't help, two doesn't help also, so you would have to do three, okay? So, this was so the one particle irreducible diagrams. Now, okay, as I said, so you can generalize this to n particle. I don't write it down. Okay, so the other notion that I want to introduce is the loop order. So let's just write down again. So the loop order is the number of inequivalent loops formed by segments of the Green functions. So how many loops are formed by the Green's functions, okay? So, for example, if you look at this diagram, well, there are only straight lines, no loop, okay? So this would correspond to 0 loops. If you look at this, well, there you have 2 loops. This and this 2 loops. 2 loops again. And this would just have 1 loop and 1 loop and so on, okay? So this is the loop order. Yeah, up to here or okay, so then let's introduce questions or no? Okay. So then just one more wording, which is the vacuum diagrams. And these are diagrams which contain an interaction vertex which is not connected to external legs. So this is the notion of the vacuum diagram. So are these diagrams vacuum diagrams? No, because I mean we constructed them in the way that we said, let's connect them to all of the interaction vertices to external legs. But these here, we actually constructed just in this way by saying, well, let's look at the combinations we can get by attaching the external lines just to one interaction vertex while keeping the other one isolated. So this clearly consists of diagrams, maybe this part here, where the interaction vertex is not connected to any external lines or legs. So this would be the vacuum diagrams here, and in the same way these here. So these would all be vacuum diagrams. Okay? And then, let's see, what I still want to say. So, this is just some words that we will need when we continue. So there's one useful thing that we will use to show that actually in a perturbative expansion we don't have to take into account all these diagrams, but just an important kind of diagram, and just make some more general remarks. What we will see is that there are typically subsets of diagrams which can be, so there are subsets of diagrams which often can be identified to be more relevant than others. Identified to be of specific relevance. So what we will find in the problem of calculating the free energy of the interacting electron gas, we will actually exactly find this. So there's different types of diagrams that give you larger contributions in some physical parameter, and what we will see is that again the density will play a role. So in the high density limit we can identify a certain class of diagrams that will be more relevant than others. And this kind of analysis is also much more simpler to do in terms of the diagrams than doing the algebraic connection, because there is another important point that often actually, and this is why also this is very successful, you can understand the diagrams in terms of physics. So often diagrams often suggest the physical interpretation of the corresponding process. And again, we will see this at the specific not only a useful way of bookkeeping and doing the calculation, but there's also often some intuitive way how to understand the diagrams, and this is of great help to understand what is going on. Okay, so that's like the short introduction into the general part. Then, okay, next lecture I still mention some kind of general aspects of perturbation theory, diagrammatic perturbation theory, and then we come back to the problem of the electromagnetic progress. Okay? And, ok, se vocês podem falar assim na quarta, se deveríamos fazer uma vez em vez da aula para discutir os exercícios, ou melhor esperar, avisa.